Hello, my name is Aaron Hall, and I'm going to be doing a presentation on transformations of sines using other functions. So the first thing I want to do is I want to talk about the general transformations of sine, and then we'll introduce other functions. For example, so if I have a function y equals sine of x, then graphically that's going to look something like this. We start at the origin and then we oscillate back and forth over the x-axis. The x-axis is my principal axis. This is my principal axis. And we see that, we're going to oscillate from -1 to 1. Now, there's all sorts of different kinds of transformations that can take place. So if I have something like, these are the transformations that I can have. So y equals a times sine of b times the quantity of x plus c plus d. Now a is the amplitude or the height of our wave. We can also call this the vertical stretch. The vertical stretch. And if it's negative, if a is greater than 0, that would be positive, then we're looking at a normal sine function. So this would be normal. If a is less than 0, if a is less than 0, then we have a vertical flip or a vertical reflection. Vertical flip. All right, b, we can see that b is inside of the function rather than a being, we're multiplying to the function versus in the function. If we do something to the function, it's vertical. To is vertical. And if we do something in, then that's going to be horizontal. So we see that a, we multiplied something to the function, so that's going to be a vertical stretch. B is in the function. We've replaced our something inside. Here, this value here is in the function. I'm just getting sloppy now with my writing. That would be something in the function. And if we do something to the function would be to all of this, right? So like a would be on the outside. So we're doing something, b is in the function. So we have a horizontal stretch, And if b, we're doing b now. If b is less than 0, then we have a horizontal flip. Horizontal flip. Then c, again, c is something in the function, so this is going to be horizontal. We are moving the c, we're adding something in the function or subtracting. That would be a horizontal shift from left or right. Now, I should also mention that when we do something in the function, it's the opposite of what we would expect. Like, for example, with b, I would expect that we would have a horizontal stretch by a factor of b, when in fact we have a horizontal stretch by a factor. I'll just write it over here, by a factor of 1 over b. Again, it's the opposite of what we would expect. And so with c, if I add, say 3 or 5 or 10 or something like that into the function, it seems like because we're adding, it would be a shift to the right, when in fact it is a shift to the left. So c is the horizontal shift, And so if a is positive, then to the left. And if a, I don't know why I'm obsessed with a. It's not a, it's c. This is c. There we go. That's much better. And if C is less than 0, then this is to the right. Okay, so let's look at D. D, I'm adding something to the function. I'm taking all of this function up here of my sine function, and I'm adding something to all of this. So that's to the function, which is vertical. So this is our vertical shift, up or down. And because it's not in parentheses, if it's plus, then it's going to be up. If it's minus, it'll be down. There's no funny business. So then I have D equals a vertical shift by D units. If D is greater than 0, then up. If D is less than 0, then down. All right, so this is really important when it comes to transformations. It's really important, or I should say when we're combining functions, these ideas of transformations are really important. So I'm going to cut this, I'm going to bring it down here, and I want to explore some ideas. Now, let's look at let's do this equation. So if I have y equals 2x times sine of x, now I see that I'm multiplying it looks like a linear function, right? We have a linear function right here, and that linear function has replaced my a value, which is my vertical stretch, right? That a value is my vertical stretch. If you recall back here, a is the vertical stretch, and I've replaced a with a linear function. And so what that means is that we are going to stretch up this sine of x is going to be stretched up to this linear function. Well, what does that linear function look like? So I also want to mention that what I'm going to be doing, these are really just sketches. And the difference between a sketch is that it's sort of like a rudimentary image of what the graph looks like, as opposed to draw. If I wanted to be more precise, I probably should use a table of values and plug in, I don't know, -1, -2, we could do 0, 1, 2 as well, and find those points to have some better precision. So I'm not really looking at precision, I'm really just looking at these ideas of what happens when I combine different function families. So I have this a value, I'm replacing a, which is my vertical stretch, by a whole entire function. So let's look at what that vertical stretch would look like then. So here's my graph here, and my function of y equals 2x, that's my a value, right? That is, I see that I have, my slope is 2, so 2 up, 1 over. And so it should look something more or less like this. We'll do the same thing down here. Now, because this is my amplitude, when I draw my graph, I'm going to start at the origin, look just like I do with all my sine functions. And then when I oscillate, that amplitude is going to be what the graph goes to. I end up going way up here, right? So it looks like my sine function, it grows as we oscillate back and forth. And then I guess the question is, what happens over here on the left-hand side? Well, if we look at sine, if I'm rotating clockwise, then sine, which is my y value, is going to be positive here, negative here. Well, what happens if I have negative thetas or negative angles? Then I'm rotating this way, which would mean it's negative. Now also, if I plug in a negative x value, then that's going to give me a negative here plus times a negative here, which is a positive. So on the other side, we're going to get a graph that's going to be sort of the mirror image. Right, so that's what the graph looks like. So So 2x times sine of x would look like this. What happens instead of multiplying? What if I add it? What if I add? So if I have something like this, I have y equals 2x plus sine of x. Now let's go back and look at our transformations. And if I'm adding something to my function, isn't that my d value? And if it's the d value, well, the d value is my vertical shift. And so that means, what it means is that this line right here, my principal axis, that principal axis is going to be shifted up or down. So let's go back down here, and I have, so this would be now my vertical or my principal axis. This is my principal axis. So we'd have our graph. We're going to draw our line then. This is a linear function so y equals 2x with a slope of 2. So 2 up, 1 over would look more or less like this. And then we're going to be oscillating up and down across this. So we always start with, for sine, we're going to start at the origin, and then we're just oscillating back and forth across like that. That becomes the principal axis. That's sort of cool. Sort of cool that it does that. All right, we could do that with anything, right? We could do something like, y equals x squared plus sine of x. Well, that's a quadratic. So our graph is going to look something like this. And then we're oscillating. That is our principal axis. So we're going to oscillate back and forth over that principal axis. So it should be something like this. So let's look at what happens. Let's multiply. Let's make this our amplitude again. So instead, so I have y equals x squared times sine of x. So this is no longer my principal axis. This is my a value or my vertical stretch. So in this case, if that's my vertical stretch, let's draw this out. This is going to be my graph like this. And so we're going to be stretching up to that amount. So we're going to be going something like this. And then we ask ourselves what's happening over here on this other side. Well, what if we plug in a negative value over here? Then because sine in the fourth quadrant is negative, then this is going to give me a negative value, but this gives me a positive value. So it looks to me like this is just going to, it should not be the mirror image on the other side. We should end up going down and then back up like this. All right. So, what else could be interesting? What if we combine, what if I did something like this? What if I'm sort of running out of room here? So I'll just move over here and go to the top. What if I have absolute value? What if I have something like this? Y equals the absolute value of sine of x. Well, if you recall, absolute value makes everything positive. There are certain quantities like distance or speed that will always be positive, and that's the whole point of absolute value. So that means then that all of this sine value is under a square root, which means that my y value has to be positive. So let's go ahead and sketch our graph. This is our sine of x, this is our y equals sine of x. And if y has to be positive, then our graph is going to look like this. It's going to go, here, let's use a different color. It's going to look something like this on the other side too. So if I have, let's just draw this out. It should be something like this then. Everything's going to be positive. It's Nessie, right? From, from Loch Ness. All right, so let's do another one. What if I have, let's do y equals x cubed plus 5 sine of x. So this is our principal axis. We are adding something. So our principal axis is going to look something like this. So we're going to be oscillating up and down over that line. And it looks like my amplitude of my function is larger. So for our sketch, we're going to make it higher than our previous unit of 1. And so we're looking at something, something like this. And we have to make sure that this is a function, right? It looks like a little bit, maybe if I drew a vertical line, it would violate the vertical line test. But the idea is that that the sketch isn't done that way, so that I would not violate the vertical line test for this. So let's do, I feel like I've gotten most of the big ideas. And the only thing that I really did for these transformations was to really replace my amplitude, and I did D. I mean, there's certainly other transformations that can happen when we plug in a linear function or a quadratic for B or C. Those are going to give you a different result. But the big idea of this video was really replacing your vertical shift with some other function family, or replacing the amplitude. And we get some really cool things that you see in physics by doing this. And one of those ideas is that, you know, if you have like a pendulum that is swinging back and forth, that we would expect that over time that this is going to stop. And so you're going to get something that looks like, looks like this. In fact, it's going to turn out to be exponential. And so let's do one more before we finish this video. What would this look like where there's some type of exponential decrease like this? And we're looking at the amplitude. This is our amplitude, the height of our wave right here. And so with our y equals sine of x, we're going to put something in here for our a value, some exponential. Now, if I use something like y equals 2 to the power of x times sine of x, then that's a function, an exponential that grows, right? So we're going to get something that looks like this and ends up growing over time. But what if I want it to shrink to represent a pendulum as the pendulum slows to a stop? And so I'm going to use something that would be, maybe I'll use a negative, right? If we recall what happens, that would be my b value, right? I'm making the b value negative. I'm doing something in the function. I'm multiplying by a negative in the function. That's my b value. And we go back here to looking at our transformations. Our b value, when I do something in the function, I'm doing something in the function here to my b value. That's going to be my horizontal stretch. And if it's negative, it's a horizontal flip. So that's pretty important for understanding how to do this particular problem here. So that would mean that I'm going to have, let's have a starting point of something greater. Let's do y equals, I don't know, how about 10 times 2 to the power of negative x times sine of x. And so what that would look like is we're going to be starting, as I said, this negative axis is going to be a reflection across the horizontal reflection, so it should be this one here. And we're starting at 10. That's going to be my initial point here. So at least for my exponential function, right? For our sine, we always start here at that 0, 0 point. So I actually pushed save on accident, so hopefully, all right, there we go. So I'm going to just sketch out my exponential. My exponential should look something like this. And I don't claim that this is a drawing, it's really a sketch. So we're going to have something like this. That replaces my amplitude. And then we start at our, for sine of x, we start at the origin, and then we're just oscillating. Let's oscillate up and down to our amplitude. So that would be a really cool way of representing that pendulum. Hopefully this video was helpful. I hope you have a wonderful day and best of luck on your homework.